All right, everybody, we're coming in slowly. We missed a class, I guess, on Thursday because of a snowstorm. I assume they've done that because some classes may be conducted in person, and so they probably thought if we didn't cancel off campus or online classes, but only cancel the in-person classes, that may result in some imparity, and they didn't want that. I assume that was the reason that why we didn't have a class on Thursday. All right, so we're back in, I guess, in session. And I see that the class is slowly sort of like filling up. We got about 13 students right now. And I anticipate that number will increase fairly quickly. Now it's up to 15. And I want everybody to keep up with the class and with the semester and with all the pandemic issues that we're confronted with. And I hope that everybody is in good shape. And if you are on campus for any reason whatsoever, you understand that, there's been some upticks in the number of cases on campus. This is what we hear from the people in the upper echelon. So try to be careful with whatever you do. Just caution, I think, is the name of the game in these very hard times that we all live through. All right, so what we're going to do today, we'll try to complete, if as much as possible, our task at hand, which is to, basically complete the discussion of VESP architecture for the time being. And what that really means is that, I got to get back here for a second. We will now transition to VESP 2.0, which is the next architecture in the, I guess, sequence of VESP architectures that we're going to take a look at. And as usual, I'm going to share my iPad with you, and then we'll just put another lecture ID here. It'll be, I guess, our lecture number 9, if I'm not mistaken. And we will go from there. Okay. Now, I assume that you guys are all coordinating with your homework submission and all the other important, things in your life regarding this class and other classes. And then you are trying to keep track of and remain with the university. That means, keep up with your classes and really keep alive. I mean, just stay alive, basically. That's the name of the game. All right, so here we go. And here's our lecture stuff for this particular course. We began with all these nice diagrams, and we're going to have to go all the way to the end now. Let's see if I can just do this, go a little faster this way. I don't know how to bring it to the bottom, but maybe at some point in time I'll open a new file. So this was our last class, and you probably saw me, basically use a copy of this program from a file that I created earlier to execute this on the actual VESP simulator that we all have. You have it, I have it. Everybody has a copy of VESP 1.0 all the way up to 3. I guess 2i or some such number, where we have all the additions of this architecture that gradually gets to be more and more complicated and more complex, as we intend it to be, because we want to start with simple ideas and then gradually build our way into something that's a little more involved.
Professor,
All right. Yeah.
I think there's some people in the waiting room.
There are some people waiting there. Okay,
Unless they were admitted.
Okay, I'm just going to click on this. There's one student. I think Maria is the only one. And we just let her in. I think she's in now. Yeah, I think if you log in from a place where, here, okay, so that more students are coming in. If you log in from your normal university place, I think you would not have any issues coming onto this Zoom site. I think you'll be automatically included. But if you somehow, because of some constraints that you're in, you have to log in from some other, IP or some other place, that may just cause you a little bit of a wait. And I appreciate anybody telling me that some people are waiting out there. Okay, so that's a good thing that Yekta is right there. And so is Jasser and Gabriel and Ron. Good to see you, everybody. You know, we may turn off our, I'm not asking you, but I may turn off my video once in a while, just so I can take the sip without, you know, in the privacy of my, my little room here. But if you don't mind it, I don't mind. I mean, I think sometimes it also interferes with the IP traffic here, but right now we're in good shape. So I'm not concerned about it at this moment, but at times, you know, at certain times I may end up basically turning the video off just so that we can focus on what I'm writing. Good tea in the morning. Actually, it's not in the morning anymore, but it's for me, it's a little bit morning time. Okay, so we're going to make another lecture, which will be actually our lecture number 9, from what I recollect. And we're going to go into now a more powerful von Neumann architecture. And that will be, okay, we will be, you know, let's just say that we will enhance VESP 1.0 by adding 8 more instructions to it. And you're already familiar with this because you've been doing the homework and you know that we can always add instructions. Okay, this will simplify this enhancement will eliminate the need to self-modify VESP programs. As you know that last time we had to use a pair of move instructions in order to be able to actually get some kind of an indexing taking place. So one of the very, I guess, outcomes or byproducts of making this enhancement is to give us the capability to avoid using self-modifying code, because we will now have, as you will see in just a second, what's called an index register. It's sort of like a special register that all computers today, all commercial products, you know, computer chips happen to have, either one of them or several of them. In fact, I'll give you a so-called code mill or code appeal architecture where you can make just about any register that you choose, you desire an index register. And that way, you know, and a lot of these commercial machines also have that same capability. It kind of gives you this, you know, a multitude of index pointers if you wanted to have some sort of a, you know, like matrix addition, matrix multiplication, some matrix operations where you have to have maybe more than one index continue to update itself, like, you know, some nested loop, whatever it may be that you're doing. All right, so so let's look at this VESP 2.0 architecture, okay? So instruction repertoire, you know, as we call these things instruction set architectures, the ISA, let me just, you know, decode this for one, instruction set architecture of VESP 2.0. So this thing, this machine, VESP 2.0, is actually what we call backward compatible. What that means is that you can write any program in VESP 2.0 and it will actually run any program that you've written in VESP 1.0. So that implies that all of the instructions that we had in VESP 1.0 are also instructions in VESP 2.0. If we sort of like deviated from that assumption, this machine will not be upward compatible. Now you can define backward compatible. Okay, so let me just say that VESP 2.0 is backward compatible. That means any program that runs on an earlier edition of VESP architecture, ISA really, I should say maybe ISA. So we get to use that. What is happening here? Would also run, or will also run. Just losing my thoughts here a little bit. And of course, there's only one edition of VESP that is prior to this machine. So we're talking about VESP 1.0. Okay. So this general statement really is if we were to have some other machine that's maybe even earlier than, it would have been somewhat not earlier, but simpler than VESP 1.0. And that would be, also VESP 2.0 would be backward compatible with that machine as well. So that's the idea. Sometimes you can design machines in a futuristic way so that they actually become upward compatible, meaning that you will design this machine to basically be stretchable or expandable in time. You will include these instructions in the case of ISA, which will not be functional in the present edition, but they can always be activated as in fact you build, further editions of this machine. And this is particularly useful if you're an architect of a computer and you simply have this vision that you want to have this, powerful machine, and you put in place all the instructions that you want to ultimately have, but you don't really have all those instructions quickly in place. Case in point is, for example, there was a machine that was built in 1970s and it went by the name of ENEE350. This was actually some kind of a parallel computer, or as they call it, single instruction, multiple data machine. And the architects intended to make it a 256 processor engine or a computer, but they couldn't quite get there. And so they had one quadrant of all the 256 processors built in. But if somebody wanted to make this at 200, so that was upward compatible. That's what I'm trying to explain this with. So you can always add the remaining, let's say, 192 additional processors. In other words, put 3 more quadrants into it so that you will have 256 processor system that they initially envisioned that architecture as. So that will be like upward compatible. Let me just write that, sometimes people confuse these terms, and so that maybe this will be something handy for you in case that you get an IBM interview or maybe Intel interview, something. Okay. An ISA is called upward compatible if it can be extended to, excuse me, future ISAs without altering or changing its instruction repertoire. Okay, so you would have or base architecture, which is to say, in the case of like that thing that I mentioned to you, let me just erase this. You could extend, basically, you can extend the architecture. You can make it so that, okay, you can make it more powerful without, like, how it is, like sometimes they sell these products, like you create shelves and you feel like you don't have enough, shelves. And then you go to this place, like, stores like IKEA. I'm not trying to advertise anybody here. You go there and then you buy another piece and all of a sudden you just stretch it, another level or something. So you don't have to take apart the one that you have. You simply add to it. This is like what's called upward compatibility. Okay, so you make it like, modular in some ways, as Iliac 4 was, so that you can keep adding more and more boards or racks or maybe cabinets, depending upon, because in the past, these machines were built into cabinets, into some spacious rooms. Think about ENEAC, for example, that was built in 1945, the very first computer that was built, I guess, Eckert and Mauchly at University of Pennsylvania, the Moore School of Electrical Engineering there. And that machine took so much space, it was almost like put place in some kind of an auditorium size space with all of its pieces. And believe it or not, yet it was not a von Neumann architecture. That machine was followed by ADSAC, for example. That machine ADSAC was in fact sort of an architecture that was created by von Neumann. There's some debate about this stored program concept, which we've been tapping here all this time. Like even that first program we've written, we stored it in a computer memory and then executed with the help of a program counter, as you know. That was disputed somehow because I guess John von Neumann was a contractor or a consultant to the Department of Defense back in those years. And the history tells us this, the annals of histories, like there are some journals like that. If you go back to those, you will find out that John von Neumann sat in some of these meetings that took place at the University of Pennsylvania's Moore School of Electrical Engineering, where Mauchly and Eckert and their company, some other people that were involved in the design of ENEAC, were basically explaining to groups of people how to use this ENEAC computer, which is the one that they had built and that was operational at that point in time. But then the Department of Defense also asked them to actually think about making this computer more versatile, more flexible, more powerful. Just put yourself back in those years, right? That the World War II just ended, and there's some space to breathe. And people are now wanting to leap forward, like the Mars mission the Perseverance mission we just had, right? Chinese are up there also, as you probably know, right? They're just waiting to land. And I think Saudi Arabia also has some sort of Mars mission. There was a bunch of people. But anyway, just to go back to that time period, what happened was, this is all from history. I wasn't there to actually witness this. So I'm telling you, like what I read about this incident. And the reason that I brought that up is, I guess it connects with, the store program concept and architectural definitions and how we make things, upward compatible. ENIAC wasn't a machine like that. It was not, store program concept. It was, EDVAC, I guess, was created. EDSAC, I think. Now, did I say EDVAC? EDSAC. These words also get confused sometimes because what happened was after EDSAC was completed, EDVAC was then introduced in, I think it was in Cambridge, some other place. Anyway, the point is that people sometimes think that we give too much credit to von Neumann because people are now claiming that Mauchly and Eckert, EDSAC, I think the machine is EDSAC, they were basically, they had the idea of store program concept, but they never really wrote it down. And it just befell upon von Neumann to write this document, which is about 100 pages long, where he actually sort of like spelled out and wrote everything that you would think, if you read it carefully, that it is a contemporary machine. It has a memory, and then he calls instructions orders as opposed to instructions. The word instruction wasn't in his vocabulary back then. He used the word order to somehow refer to something called an instruction that we do here. But he says orders will be stored in memory. That means like programs will be stored, instructions will be stored in memory. But people disputed that he actually listened to all these conversations as the Defense Department instructed this University of Penn people to actually basically switch to another kind of machine make it, more versatile. And then because he was the consultant to the Department of Defense, von Neumann used to go there and listen to all the presentations. And then as a result of which he heard all the conversations people are claiming. And because he was mathematically so diverse and astute, he was able to write all this stuff into one document, which then became, that they call it the first draft. You can actually see this, all of this on the web, that made, the machine, so-called the von Neumann architecture, as I told you earlier. But, a lot of people dispute this edition of the story. They say von Neumann was indeed that, incredible brain. He knew exactly what he wanted to describe and what was missing in all these discussions that he heard. And he put all that things together just to make a very solid, cohesive one, architecture, which now is known as von Neumann's architecture, which is to say a program counter, store program, a separate ALU in a separate control unit. And this is with the, I guess, the IDVAC, it became somewhat of a, what they call a, von Neumann architecture. And to separate that from what is called the Harvard architecture, where instructions and data are kept in different places, they called it, they made that second machine, which they also is a store program, but it is different from the von Neumann architecture, and they called it what they call it, because it was developed at Harvard, they call it a Harvard architecture. And of course, we can call von Neumann's architecture Princeton architecture also, because von Neumann at the time he was doing all these things was actually employed at the Institute of Advanced Studies at Princeton University. So, history is interesting. And once in a while, I may just simply sample it here so that you guys get a little bit of a, instead of making a one full presentation of history of computing, once in a while, I may just, bring it into our discussion. So let's go back to VESP 2.0, which is a von Neumann architecture. So here are the so-called 16 instructions, okay? So let's just define the opcodes, first of all. Okay, operation instruction maybe. So now we're going to have to use 4 bits. All these instructions from 0, 0, 0 to 0, 0, and that is 0, 1, 1, 1. Same as VESP 1.0, okay? No different. All these instructions, like it ends here with a halt. And this is our add instruction. Okay. JPS and so on. All right. So the remaining instructions are the ones that, now we will now include in this architecture. So from 1, 0, 0, 0, all the way to 1, 1, 1. Okay, 8 more instructions will be included, and these will be increment. That will be increment. That means A will be A plus 1. And the next instruction will be decrement. That means A will be equal to A minus 1. And the next instruction will be AND. And so that means A will be equal to A and B. And then the next instruction will be inclusive OR. So A will be equal to A or B. Let's just keep these lines in place. Okay. And the next instruction will be shift left. That means A will be equal to A shift left. And the one after that will be shift right. Means it will be like this. This will be actually this guy here. And then the next instruction will be what we call MXF. That means move from with IX. I will explain these. And the last one is MXT. And this will be move from, not from, but to with IX. So now we have 16 instructions altogether, as you can see, the first 8 of which are exactly the same as before. And that's what makes this machine completely backward compatible with VESP 1.0. So let's understand these instructions that we just added, because the other instructions we actually have created. And let's also, for just a brief minute or brief maybe second, I don't know, maybe a couple of minutes, think about, how we would take VESP 1.0's hardwired controller, one hot design, and make it like this machine's design. Okay. Let me just say an aside here. We can easily, maybe I just say note. We can easily extend the microsequencer or the controller of VESP 1.0 to handle VESP 2.0 instruction. Now, instructions. You know that the first 8 instructions are identical. So all we have to do is to put this, decoder, just simply put that, replace that decoder, or maybe put another decoder 3x8 or something. But, best thing would be to have this decoder now have 16 outputs, right? Here is your 4 inputs, IR0, IR1, IR2, and then IR3. Okay.
Professor, can you go up a little bit?
Yeah, sure.
All right, thanks.
Mm-hmm. And then we're going to have now 16 outputs as opposed to 8. 1, 2, 3, 4, 5, 6, 7, 8. This will be exactly as before. Okay, these will work. These will work. These work exactly the same as before. These are like VESP 1.0 instructions, the first 8. Okay, they're basically like, I guess, add, complement, etc. Okay, and then halt right there. Now the remaining 8 instructions, will have their own little bit, like action. For example, let's put this one. This is like, A's increment. All you have to do is just excite the ALU with an A on the left input and 1 on the right. That means now you have to put a little multiplexer in there. and then do this A equals A plus 1. And for, A minus 1, you just simply add -1 to A. So that's like increment, decrement. My desire is not to do these. I'm just simply telling you that at the very bottom you have MXF and MXT instructions. So you can develop, and these will take a little bit more time because they actually have to do a number of small steps in order to be able to get these instructions work. But increment, decrement, shift left, shift right, and then or they can all be done in one clock cycle, just like the add instruction, just like the complement. These are very similar. All of these instructions up until here, which I think we will end at shift right here, the last one, they are very similar. Not exactly the same, but they are very similar. So far as execution, okay, so far as their execution. It's concerned or something. You write something there for yourself. I just turn out of the margin there. Okay, it's these instructions are a little different. Okay, these require a little more work. Again, our focus is not so much to really see how this gets done in hardware at this point in time. We just want to know what these instructions are, and implementing them is not a big deal. It's like the same architecture that we had in VEST 1.0 with a bigger decoder, and those last two instructions requiring a little more attention than the increment, decrement, shift left, shift right, and so on. Okay. Now, so how is this, different? The last 8 instructions, what exactly are they? And it doesn't take a lot of energy to explain these things like increment, decrement. Those are obvious. And then or instructions are bitwise. Okay, so but just to give you an example of maybe 1 or 2. So some examples here, so you know what really happens. Okay, so let's look at this increment, what exactly it does. It simply says A equals A plus 1. Okay, so if I were to think about some simple, some small number in A, some number. Okay, so let's write this number 1 0 1 1 1 0 0 0 0 1 1 1, and then maybe 1 0 1 1, something like this, some number. And if I increment this, so that's A plus 1 will be just this. Okay, we just want to add 1 to it. So what happens is, you can see when you add 1 to it, like you'll get basically 0 0 1 1, and then you get 1 1 1 0 0 0 0 1 1 0 1 1. So now this was actually 11, right? That's actually yep, that is 11. That would be B. That is 8, and this is 7, and this is also 11, which is B. So our number was B8. Let me just write this like 8. Okay. And the number that we get at the end of this is obviously going to be 12, which is C, then 7, then 8, and then B. That's how this number is supposed to be. Okay. And, without going through the mathematics of it, you can see that A plus A minus 1 would be, on the other hand, if you subtract from this number 1, then of course B will turn into A, and you will get basically this number. It will be just B8 7A. So that's how you'll get these numbers, like work. Okay. And then, there is, or and all those things you know how to do. I'm just doing these examples only for you to understand what exactly we mean by, oring two registers, what we mean by ending two registers. Let's just put an example. Let's maintain this number. Okay. So we had this A, which is equal to, 1, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. And let's put another number like B here, maybe 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, maybe just 0, 0, 0, 1, something like this, just some number. Okay, so if you just look at A and B, then you get basically 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, triple zeros, and then a 1. And you do A or B, then you get 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, 1. Okay, so now we explain these operations. The only other operations that are actually logical or data manipulation wise are shifts. Let's take a look at these shift instructions. Okay, so let's just use that A as we have. Okay, so again, I just want to write, this here. Okay, so let's look at this A one more time. 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. Then we want to left shift this number. Okay, so if I do a left shift 1, then 1 disappears, and then we get 0, 1, 1, and this one goes over here. I get 0, 0, 0, and that 0 goes over here, and that 1 gets here, 1, 1, 1, 1, and another 1, and then 0, 1, 1. And now we have to stick a number in here, which will be 0 inserted. And then what happened is discarded. Okay.
Professor.
Yeah.
If we continue this for several times, would we end up having all zeros eventually?
Yes. If you keep shifting this left, I guess 16 times, you get nothing but zeros.
If there was a what would a comment be like?
Let's call it, huh?
If you had a loop of having like whatever we take on the go to the end, what would that be?
That's called a rotation. This is a shift. So we can rotate a vector like this, or we can shift it like this. You see the motion of my hand? One is shift, one is rotation.
Could it be possible if we would have, when we are shifting, we would have been 1 instead of 0?
When you shift with, the right-hand side, you never put a 1 on the right. As we look at the right shift, which is the opposite of this, we will have two different kinds of shifts, one of which will be actually what you said. Yeah. Now, what happens every time you actually put a 0 to the right of this sequence, you're multiplying it by 2. But when you keep doing this 16 times, you just multiplied it too much. And therefore, that bit that was significant ended up basically, moving out of your domain, and you don't have that number anymore. Now, if you kept an extra bit to simply store that number bit in that particular, flag or bit flip-flop, then you can still say you multiplied it by 2. But what would you do if you just shift one more time? Right? That will also disappear. In other words, you can't have exact representation of infinitely many digits in any finite system. Now, they call most of these machines Turing complete. Okay, anybody heard about this term Turing complete? You heard about the name Turing, Alan Turing, like the person who's, you know, they made a movie about him. Never saw that movie?
Yeah, I've seen the movie.
You saw the movie,
Imitation Game. It was pretty good.
the halting machines, right? So Turing, Alan Turing. Turing machine complete means that you can basically simulate any Turing program on a computer like even VESP. Okay. The only thing that is critical here is that, you know, we just add the assumption that we have an infinitely large memory. If you make it infinitely large, then all of the operations that you can actually perform on a Turing machine, which is basically to go one place to the right, to go one place to the left, right, to enter something into the position or remove something from the position, all those things can be done in the VESP 1.0 will take care of it. I think there is a machine with only 4 instructions that is actually Turing complete. There's a lot of stuff, you know, like you're taking classes from all kinds of directions. That's why you are in a university program. You're not going to become a technician at the end. You're very smart already, but you're going to be even smarter because you take all these different classes and you put all these information together to make yourself a one whole person, professionally speaking now. Okay. So when you're looking at things like this, you always like, you know, keep all the adjacent blocks in view, you know, see how they're all connected. Nothing is isolated. Okay, let me just go back and then, you know, keep talking about this. So let's go and do this. You know, this was actually left shift, right? Let's just write this. So in left shift, that's what we get. Now, if you look at this, these as numbers, let me just do this so that you understand, you know, what we're doing here. I'll just take a smaller number. You know, let's look at maybe an 8-bit number, 0, 0, 0, 0, and then maybe, you know, like 0, 1, 1, 0. Okay. So what happens if I shift it by 1 bit to the left, right? So I put this 0 up here, this one there, this one here, this one goes here, this one comes up here, this one goes here, this one goes here, this one goes here, and then I put another 0. So all of a sudden, the number 6 has become number 12. Okay. So that 0 insertion on the right made it equal to 12. It was 6, now it is equal to 12. So left shifts multiply numbers by 2. So we can say in general, left shifts multiply numbers by 2. Every left shift, one shift, obviously. I'm not talking about shifting 2 times and saying that's multiplying it by 2. If you shift it 2 times, you get a 4 times. Now, this works not just for positive numbers, but also for negative numbers. Let's take a look, right? Let's say that I have something like this, 1, 1, 1, 1, and then 1, 1, 1, 0. Now, what number is this? You've studied this, right? In the ENEE350. This is equal to, algebraically speaking, minus 2, right? Everybody knows how to do that. You've seen this, and I don't want to, you know, explain this, you know, too much because then I trivialize your knowledge. I know that you know that this is equal to minus 2. If I were to teach 244, I would explain it to you, but I don't want to explain it to you at this point. So if I left shift this by 1, I'll get this number basically. 1, 1, 1, 1, 1, 1, 1. I'm sorry, not 1. 0 and a 0. So this number becomes now minus 4. So you can see that I multiplied a negative number by left shifting it too. Okay. So you can see that this multiplication to left, a shift to left, multiplies numbers whether they're positive or negative. It doesn't matter what they are.
Professor,
Yeah, Gabriel.
in
In this class, when we're dealing with numbers in binary, are we always going to be dealing with signed numbers, or will there be occasions where we're dealing with unsigned?
Yeah, so I guess, yeah, so the answer to the question, I mean, it's a pretty loaded question. So the answer to that question is this. It all depends on, what we're doing with them, okay? In other words, these are just numbers that we're processing. And, the instructions are aside, we're just looking at them, as like strings of bits, right? When I made this left shift, I said this number is equal to -4. Why did I say that? Well, as much as it's -4, it's also twice as big as that number at the top. Isn't that right, Gabe?
Yeah.
But it's plus or negative, it doesn't matter. It's still 2 times the one at the top. It's same rule applies whether I look at this as an unsigned number or a signed number. So the interpretation of these sequences as signed numbers is just a convenience for us to be able to do, for example, signed arithmetic without checking the signs of numbers, being completely oblivious to the fact that we're looking at some bit patterns that may actually represent negative numbers. We simply add them. Maybe only when we have to print something like this for our consumption. Let's say I'm doing some, like accounting business, right? The accountant doesn't care if I'm actually adding these numbers as if like they're unsigned or signed. When he looks at his numbers, he wants to see that negative number in there. So it's in the translation process, in the display, I can certainly make these numbers look as if like they're negative numbers. And both of them are negative, if in fact I want to think that way. It's 2's complement, basically, what we're using here. So, the question is a pretty good one, but it's also one that really begs, this thing that I try to explain. What do we see when we look at a bunch of bits? Does that make sense?
Yeah, and I think kind of part of the reason I asked is like when you look at these two numbers here, -2, -4, in sine 2's complement, yeah, -4 is 2 times -2. But then if you're just purely looking at the bits, you're like, oh, well, -2, or that number looks larger than -4 there.
Oh, yeah, right. But you know how that works, right?
Yeah, yeah.
In the negative scale, the most negative number is the smallest.
Right.
Right, as this sort of like begins to show that. As the bottom number, magnitude-wise is smaller than the number at the top. But as unsigned numbers, the one at the top has been left shifted. Actually, not smaller. What did I say? Yeah, it is. I'm sorry. But you left shift that number and you ultimately get, if I put this bit here, that that this number is bigger, right? I just do that. That's what I really meant. Sorry about that. Delete.
So you're basically saying it's not going to increase, not necessarily increase the value. It would just multiply by 2. So if it's negative, it may like be less. If it's positive.
What I'm saying is basically, like when I make a left shift, like this number is shifted by 1 bit to the left, right? So what happened to this 1? It's there, but it isn't there. Clearly, this number was 0, 1, 1, 1, 1, bit, etc. And of course, this number is greater than this number. Just because I dropped that 1, which was on the left, because I can't see it, right? That's the point. The point is that, yes, the bottom number is actually still bigger than the top number if you consider these bits or take them into account. Okay. Otherwise, you can see that, without that bit, this number is greater than this number because they have the same number of bits. And these bits are identical, but there's a 1 in there, but there's a 0 here. So this must be must be greater than this for sure.
If we do right shift, would we be dividing by 2 then?
Dividing by 2, except that when the number is odd, we lose that remainder. Gabe, are you comfortable with all the things I said since the last comment you made?
Yep, sounds good.
Okay. All right, so now let's take a look at the right shifts, okay? So now let's take a look at that same A. Actually, the one that we had earlier. Okay, 1011, 100. What are the other ones? 0111, 1011. So now we take a look at, right shift. So this can happen two ways. And in VESP, we actually use what we call arithmetic right shift. That means we actually take that sign and insert it back so that it remains. So there are two ways, two options. One is what we call arithmetic shift, right shift. In which case we have this number. Okay, we're going to put that 1 back in. 101. That 1 will go to the right. It become 1100. That 0 will travel to the right. 1 1. And that 1 will go to the right, which will make it 1101. Okay, so that is exactly what we said it would be, except that the division will be not exact because the number that we divide by 2, divided by 2 in this case, is not actually an even number because there's a 1 at the. This is an odd number. Now in the right shift, okay, so in this case, reinsert the sign bit, okay, on the left. In logic shift, logic or logical maybe, right shift. Insert a 0 on the left. And everything else it remains the same. Okay. So we have now 0 1 0 1 1 1 0 0 0 1 1. I'm sorry. 0 1 1. And then 1 1 0 1. Okay, so this is inserted here. Okay, this is the sign. So let's look at some, simpler numbers and see how this does what we just thought it will do. Okay, so let's just do a couple of examples like we did. Okay, small numbers. Let's say that I want to have a number, another example.
Professor, for the
Yeah,
arithmetic right shift, what if our number was positive?
same thing. You put a 0.
Okay, so what's the second one called again? Logical?
Arithmetic, logical, yeah, logical right.
So
Logical right always places a 0. If it's arithmetic shift, then you take that bit, whether it's 0 or 1, you put that bit back in. So if it's 0, you put a 0 in. If it's 1, you put a 1 in. Yeah, it's just that bit, whatever it may be, you put that back in. That's your arithmetic right shift. So let's take a look at this. Let's, maybe look at some simple example. Okay, so here's one number. Okay, make this number here. Pretty much the same number we had before. So this is actually -4. But if I right shift it arithmetically, then I get basically 1, 1, 1, 1. That 1 goes over here. And that one goes there, that one goes there. So 0 gets destroyed, and I get this, right? So this goes off. Removed, deleted, discarded or whatever. So you get basically this number, which is equal to -2. So that's like 4 divided by 2. So you can say, you can say that, like this has the effect of dividing. Now, the problem is that if you had a 1 in there, that will be destroyed, that will be removed, and you will not have an exact division. But it will be the quotient. It's because this division is not exact. You cannot expect to divide a number which is not evenly divisible by a divisor and get an exact value. There's nothing unusual about this. You just simply, either you have to maintain that remainder of 1, or you simply say, I don't care about the remainder. I'm only looking at what's called an integer division. So like in this case, if I had 1, 1, 1, 1, 1, 1, 0, 1, that will be basically -3, right? Because that's 13. Right, that's equal to -3. And if you right shift it, okay, let's just right shift it by 1. Let me just write this here. Then you get this, right shifting it with the bit 1, 1, and then, like those 3 ones get here, and then you get this one there, this one there, and this one there, and a 0. So you get a -2. Okay. So I guess you can think of this number like this then. -3 is equal to 1 times -2 minus 1. So that the remainder agrees with the dividend. That's how this division works. So we can say that the sign of the remainder agrees with the sign of dividend. Dividend meaning this. That's the dividend. And this is the quotient. And this is what we call the remainder. All right, everybody. So you follow this, right? So we've done shifts, left and right shifts, and we did arithmetic shifts versus the logic shifts. Let's just look at any questions up until now. Anybody? Maria?
I have a question. So if our number was much bigger than us being able to like tell right away what it is, is there a, like, for example, if it was a left shift, we would just divide it by, multiply by 2, right?
Yeah.
Is there a like easy mathematical way for right shift that we could just could we say we divide it by 2 and then we round it up?
Well, I mean, you have to know what these numbers are.
Yeah.
Right. I mean, I could tell you. Let me see if I could just maybe answer this question somewhat, like you need something like this maybe in front of you, or some web app which will show you what these numbers are like. For example, let's say that I want to just, right shift some number, right? So here's what I do. Let's say I want to load a number into, this is, let me just put this into binary. Okay. So now you look at these numbers, they're all 0 at this point, right? So there's R0 in there. Let me just make this a little bigger so everybody can see this.
Professor, we can't see that.
I know you can't, but I just realized that you can't see it because I thought I was showing this to you. But I realized that I have to now do a new share. which you will see in just a second. I am so presumptuous sometimes with my screen. I think that everybody sees what I'm doing here. Okay, now you see it, right? So get those numbers like they're all zero. Let's just do this, a couple of experiments here that we just did. R0, for example. Let me just put some number in there, minus maybe like 12, okay? Some number. I put it in there and you look at it, it's a bunch of ones followed by some numbers. That's minus 12. How do I know that's minus 12? I click on this and it says minus 12. I want to know that number is an unsigned number. What is it in, like 16 bits? It so happens that number is 65,524, right? What number is that as a hexadecimal number? It's FFF4, triple F4. What number is it as an octal number? It's that number. So this is what I was trying to tell Gabe earlier. It's like how you look at these things, right? They all look different, but they're the same thing. So if I shift, for example, one of these, like that number, if I shift it right, let's just do that, shift right by 1 bit, maybe, like I think this works, it should. Let's go back to that, decimal notation. That's minus 12, and I'm going to do that now. So it became minus 6. If I shift it again, one more time, it becomes minus 3. If I shift it again, one more time, it becomes minus 1, right? Oh,
No,
so it becomes, why is it minus? Wait, hold on a minute, because I think something happened. Minus 2, because what we said it will be minus 2, not minus 1, as we computed, not minus 1. Remember my notes? Do you remember what I did right for that?
Yeah.
Minus? Yeah. So minus 2. Exactly what we expected to happen.
So if, for example, if you had a 9, would it become 5?
Yeah, let's write that 9, LDI, R1, 5, and then let's actually shift right that by 1. Okay, let's take a look at that second location, 5. Oh, no, you said 9, right? So let's go back here a little bit. So that's 9, and now I shift it by, that would actually be, what should that be? It's like 9.
5.
And would that be 5, or would that be, I guess it'll be 4, wouldn't it? The 1 will disappear, right? I got you write 9, 1, 0, 0, 1. When you right shift it by 1 bit, what happens to that 1? Goes away.
Yeah.
So let's see. That's 4, as we expected. Well, you also expected to get a 4 in this case because you're shifting it by 1 bit. Let's look at this as an unsigned number, by the way, before and after the shift. Let me just show that to you in binary. Okay, so let's go back and then look at that number 9. That's how it looks. You see a 0 on on the left. So when you right shift this, what will happen? That 1 will drop out. What's left is 1, 0, 0. So you need something like this. As you can see, that's what happens. And of course, when I click on decimal, that's what I get to see. So you need a tool like this, and there are lots of tools out on the web. They will show you what these numbers are, whether they are signed decimal, unsigned decimal, hexadecimal, octal. We could also enter numbers in, for example, floating point, right? You probably studied a little bit of floating point, maybe not. I'll tell you a little bit. Let's just say that I want to put some number like this, 2.5. That's a number that's actually not a whole number. So when I look at that number in decimal, that's not decimal apparently. What did I put in there? 2.5. Well, floating point is what I have to look at. So that's now it's 2.5. But look what happened to my other number. It became, a very strange number. Because in binary, but that whatever number that was, that number turns out to be this number in floating point. More to my point, whatever you see is very elusive. However you interpret that is like your notation, your representation. We can look at these numbers any way we want. Right, Gabe?
Yep, exactly.
You get the idea that it's just like how we want to see these numbers. In floating point, I'll tell you, we're using what's called this, IEEE 704, I guess, format, whatever it is, 794, 1794, I think it is. And in that notation, you got a sign bit, you got a biased exponent, and you got a mantissa with a hidden bit. I'll tell you about this a little bit. Have you studied that in the ENEE350, anybody?
It
No?
was one of our assignments, I think, at the very
Okay, just
end.
an assignments, yeah. So we will, take a look at a couple of examples as I actually go through code appeal with you. We'll take up on this technology in just a little bit. We're almost there, okay? There's a lot of other stuff in here. I don't want to advertise this too soon, but there's a lot of stuff that we could do with this machine that would help us understand, what computers are all about. This is like that. The reason I call this code appeal with two E's, not a E and A, is because we're peeling the computer from top to bottom. That's what we're trying to do with this technology. And that's all, University of Maryland work, right? Basically.
Professor,
and you
where
have
can
to-
we download this?
Say it again?
Where can we download whatever you're using right now?
Yeah, that's a very natural question. There's an earlier edition of this on what we call virtual lab. College of Engineering has a virtual computer lab, and you can download a forerunner of this, which is called CodeMill. And I'm working around the clock with my programmers to actually get this ready in about maybe 2-3 weeks time, so that I would get this uploaded to our virtual computer VCL lab, and you can actually use it. There are some bugs that we're trying to fix as we speak. They're also, like, I don't know, anybody involved in this, in sort of developing things, you can see this is a GitHub project, by the way. Anybody doing a GitHub project? Okay, yeah, so this is an active project. Like we have basically lots of issues that we're trying to solve. You can see all these issues there. This is a live project that we're looking at here, which means that, whatever I give you will have bugs in it. Does that make sense? This is not like somebody actually tested this, 100,000 times and made it all work. We know that it works most of the time, but you'll be frustrated if I give it to you right now and you just see lots of issues. It says, well, I can't do this. And I say, don't blame me for it. It's in the development phase. We're developing something very powerful. We're working around the clock. Some 4 or 5 people are constantly, working on this, including myself. And our goal is to get this ready for everybody. Whether we will get it done by the time, depends on how much luck we're going to have. By the way, I will also give a talk on this one. You may actually attend that talk maybe by the end of March or sometime in April to the IEEE chapters in Maryland, Virginia, and DC. We want people to actually get their hands on this as soon as we get the first edition roll out of here. It's the University of Maryland Technology. And I think you should all be very proud of the fact that you go to school here, and then, that you take classes where technology is basically homegrown as opposed to using somebody else's work. Okay. But there's lots of things you can do. Some 9-to-6 commands. There's a huge help file here, the help place, where actually you can see every one of these instructions defined. Like there's this relative load, direct load, all these things. NOR gate that we talked about, OR gates, like we don't have OR gate and NOR gate in this VESP that we have. Lots of instructions in here. You have halt. It's a brief representation. You have exchange, lots of different ways that you can exchange. This is both an SISD and an SIMD architecture, very powerful. Some of the Intel chips today, for example, have this SIMD capability, and we put, in fact, even more powerful instructions into this. Some shuffles, some exchanges, some reverses, very, very powerful. If, in fact, you were to build this machine into an actual chip, this will be the most powerful computer in the world insofar as, what it can do. All right, so much advertising. Let's get back to work, right? Go back to where we were, which is to
Professor?
here. All right, I want you to get excited, but not too excited. Okay, you at some point in time you'll be programming this. I think you'll have a lot of fun with it. So I'm just going to get back to what we're doing here. Let's just go ahead and do that. Okay. All right. So let's just wrap this up here. What happened? There we go. The only two things that remained are what's called the MXF and MXT instructions. And I think they're the most powerful in this particular group or the architecture, because they're going to allow us to avoid a self-modifying code. So the last two instructions, VESP 2.0. These are MXF and MXT. So what are they? All right, so we add into this computer, VESP 2.0, a new register. Remember that location that I defined to be location 2, and that's where I would keep my so-called virtual index register. I call that index register. So now that becomes a permanent part of this computer. Okay, we add a register to VESP 1.0 to make it VESP 2.0, and that is this register IX. Okay. 16 bits. What does IX do? IX actually looks at a location. It is like the pointer. Whatever number that you put in there is going to point to a location. So when I have an MXF instruction, it's like this. Here's the memory that we have. And here's our IX. And I have an MXF instruction. Now remember, the move instruction or the load instruction both took up 2 consecutive 16-bit words. But here we only have this instruction, MXF, which happens to be 1110 in terms of its opcode. And here is what we call the destination address. So where is the source? The source is in here. Source is in IX. So that's why we call it MXF. Move with the index register from a location. So let's say that this instruction's address is looking at a place here. I mean, this IX register, I'm sorry, take it back. Let's say that that points to that place. So, and that this address right there points to a location like this. Okay. So what happens is this, that you copy what is in here into here by way of this move. That's what this instruction does, MXF. Okay. So in the case of MXF, IX serves as the source of our move. Whatever number we have in there is going to get us a location from which we extract the operand and then push that operand into a place whose address is given in the instruction. You know, this could be that this is the address. This is, as I said, like this points to a place like that place I'm talking about. Okay. So if this is like, you know, if I write this as to be 25, this is like location 25, maybe 125 or something. Okay, just guess. And if this is 16 here or maybe 24, this is location 24 here. Okay, address. address. I mean location. And, you know, that's the address. Now, if 125 had in it a number like maybe -36, then we put into this place. No, I'm sorry. I'm just rushing now. I can see that. That's not what I meant. Here. In that location, let me just write it here. If I have -36 here, for example, that number will come down here. Okay, so we copy whatever is in that location that is pointed by the IX register to a place whose address is given in the move instruction. This is an MXF instruction here. So MXD does the opposite, okay? So what does it do? It just does the opposite of this. And how does it work? It works like this. I need a couple of more minutes to finish this today. So we can do an example on Thursday. So here's how the, how the other instruction works. MXD. So the MXD sort of like, again, we have the IX and we got the memory down here. Okay. And this time IX points to a location. Let me just put the instruction first of all. This will be 1, 1, 1, and 1. And here's an address, okay? Now this one is going to be the source address, not destination, but the source. And IX, on the other hand, will point to a location, maybe right there, to which we have to move something. Okay, so now we're moving what the source address that's given in the instruction, shows or points to, and we move it to a place so IX has the destination. Whereas here, as I wrote it, I guess I said source is in IX. There it is, destination. And this is, instruction has the source. Okay, so if I have, -35 here or -36, they'll go from there to here. So copying process is like to move to, that's where that to comes from, with the IX. Move to a location with IX. Now, what these guys do, is this. If you use MXF, that's effectively what you're doing. So here's maybe the last explanation. What MXF does, it takes a bunch of places in your memory, maybe starting here, a bunch of other places, and they copy them to a place, for example, here. So it's like, a multiplexer, right? You basically, you move all the elements, of course, one at a time, from an array, like this array, into a register or a location. In memory. That's what MXF does. Now, this is like, multiplexing. The opposite of this is multiplexing. Okay, MXT, let's see, what did I say there? You distribute the elements of an array one at a time. No, not the elements of an array. You distribute an element, that is, to an array of locations, one at a time again. Okay. And so this is like a demultiplexer. So, you know, like it looks like you're taking this and then pointing it to lots of places, array, and, you know, that one element. And here, it's the multiplexing process. It's like you go like this. This is your array, and you go to a single place element. So it's the opposite process. MXF does the multiplexing, just remember it that way. MXT does so-called the demultiplexing or the distribution. One is a multiplexer, the other one is a demultiplexer. You know, obviously these are not circuits I'm referring to. These are instructions, but they behave as if they are multiplexing a bunch of array elements into one place. And by the way, our example, that some example that we did is going to obey this structure MXF. We're going to get a bunch of numbers from the memory, and then one at a time, we're going to put it into the B register and add it to the A register, and that will be the loop. And let me just say, in both these instructions, IX gets incremented by 1 at the end of the step. We don't have to even worry about incrementing anything. IX is incremented by 1, each time we execute an MXF or MXT instruction. Okay. I think that brings us to the end of this class. I hope that you, I overwhelmed you a little bit here and there, but I hope that you get the message. The message is we are still keeping up and keeping with the material that we started to talk about. This is just an extension. Now, I think, did I say lecture 9 at some point in time here? I think I probably did. I just want to double check. I'm going to put these things up on the, you know, in fact, I should have done that last week, right? Because I said, maybe I didn't say this class, but I said the other class, that I will basically put these things every 2 weeks on the web on Elms. But if I haven't, you know, I'm due for one of those. And then a second, yeah, lecture 9 right there. And so I will send you everything that I've done up until now, except this lecture. I'm going to wait for lecture 10. Actually, no, lecture 12, that is, because I want to do this every 2 weeks. So you should have this at some point in time, I think, at your disposal. By the time the semester ends, you'll have these notes of mine, like a little diary you can keep. And yeah, that should give you a little bit of a history of ENEE350. These are different times. I never thought that I'll have this nice iPad where I will be writing my notes in blue, red, and gray. And then, you know, students will have this as a little souvenir for many years to come. All right, I'm actually done. I'm going to relax a little bit with my lute here. As you can see, it's always in my hand. It's always within my reach. Whenever I feel like I'm done with class, right, I just have to play this a little bit. Everybody, that's not bad, huh? stop right here. You know, we're gonna always have bits and pieces of things, all right? But I'll play later on. So there'll be more, more music to come once in a while. If you just keep coming to class, this will be the added value to the course, music.
Thank you,
And if you
Professor.
guys want to practice your musical instrument anytime, let me know. I'll schedule you for one of these short sessions, all right?
Okay.
Okay. I'm done. I'll see you guys on Thursday, okay?
Yeah,
easy.
have a good day.
Thank you.
Thank you.
Thank you. Thank you.
One quick question before I leave
Yeah,
you
sure.
alone. When will the next homework be due or released, I guess?
Very soon, because I think we're just, Maria, we're coming to the end of the programming portion. The next homework will be actually, a self-modifying code programming plus this particular version. And I'll do an example on Thursday. That same problem we did on, I guess, the last week. We're going to look at the version of that same problem on VESP 2.0. And once we get these two done, I think by Thursday, I should be ready to actually roll the second homework to everybody.
Okay.
All right.
Thank you.
All
Have a
right,
good
take
rest
care.
of
I'll
your
see
day.
you.